Hi, this is Aditya, and along with my project partner Kaishavi, we'll be demonstrating our laboratory assignment 8 for the course EE542, which is on comparing Hadoop and message passing interface. So, this is the order of our demonstration video. So, first, I'll talk about the clusters basically, and then I'll be showing the Hadoop part of word count and character count, followed by MPI word count and character count program, which is being demonstrated by Kaishavi, and Kaishavi then conclude this presentation by drawing the comparison and conclusion. So for our Hadoop versus MPI comparison experiment, we created 4 nodes that belong in a common subnet, and we created this in our AWS region. So and we needed two CPU cores and at least 4 to 8 GB of memory, shared memory. So this is a cluster topology that was used. So we are using the 4 node clusters, and this is my name node, and the rest 3 are my data nodes. So as you can see, we're going to compare on the basis of the MapReduce program on both Hadoop and MPI. So I'll be first demonstrating Hadoop programs, and then I'll give it over to Kaishavi to record the MPI programs. So for Hadoop, you can see that I've already created mapper and reducer. So the first program that I'm going to run is word count with max and min. So what this directory shows is, so my text1 directory, I'm gonna ls so that I can show you guys. Yeah, sorry about that. So as you can see, the text directory one has 3 files, 1.6 megabytes, 1.4 megabytes, and roughly some 700 kilobytes. So what I'm going to do is I'm going to uh, copy this local file system to the Hadoop file system next. So the command for that is dfs copy from local text directory 1, right? So I'm gonna give this name as Gutenberg, and this is gonna create my the file system on my Hadoop, right? So just to confirm that we have that file system, I have the, so this is my public IP address for my name node instance. So to check that the file system is created, we yeah, so as you can see, Gutenberg is created, right? So what I'm going to do now is to run my mapper reducer job on Hadoop. Jar slash user slash local. Yeah, you know what? Instead of doing this, I'll just copy what I previously made. Yeah. So instead of this, I'm gonna name this as output. Instead of Gutenberg 1, I'm gonna name this as Gutenberg. Right. So this command is gonna run my MapReduce program for counting the words and giving out max and min, and on my Hadoop file system, on all the text files on the Hadoop file system, right? So it's gonna map first. It's gonna run the mapper on all these clusters, and then reduce depending on which map gets completed first. So I'm gonna pause my recording here because this might take some time, and I'll resume my recording once it's done. So as you can see, the job is completed with no errors. So just to confirm that the job is successful, we go to the GUI access and then reload this. So as you can see, this is our latest job, and you can see that it's finished successfully. So we can also check whether we got the Gutenberg output as our directory. So if we reload, and as you can see, we have our directory here. So what I'm going to do is I'm going to print out the output for the file. So do that. I'll run a command sdfs dfs -cat. Oh, before I do that, I'm just gonna check what my success file name is. So my success file name is part and 5 zeros, right? So what I'm gonna do is to print out my output basically. One, two, three, four, five, right? So when I do that, it's gonna spit out all the output, and it's gonna show that my maximum word that's the, which has the frequency of 42097, and all these words are the minimum ones with the minimum count as 1. So I'm outputting all the words which have a count of 1. So I'll show what the mapper and the reducer program does. So first, we're going to read the input file. So we are essentially reading from the stdin, right? So if you go to the main data read is read underscore input. So our read underscore input is actually a user defined function, and we are passing the argument as stdin. So it's gonna just see from the input, right? So for line and file yield line dot split. So what's gonna do is gonna split the line into words, and then what the mapper does is it basically converts all these lines into separate words with the count as 1. So we are giving a separator as tab, right? And this our mapper is gonna give out the word with the count 1, even if the word is repeating. We're not performing any logical function here. We're just gonna print out the word, and the output of the mapper will be taken as the input for the reducer, and all the logic is gonna done in the reducer. So I'll show what the reducer is. Right. So if you can see in the reducer, we can see that first I'm creating two variables, max count equals 0 and max words equals to none, and I'm gonna read the data, and I'm created a user defined function called read mapper output, and I'm gonna get the basically word comma count from the line dot strip dot split, because I'm specifying my separator as tab, right? So my data will be basically x number of rows and 2 columns. First column will be the word, and the second column will be the count, right? So we're going to use a utility called group by, which groups the multiple word count pairs by word, and it then creates an iterator that returns consecutive keys in their group. So we're using group by, and current word is basically the word key, and we have the group, the corresponding group, right? So I'm using a try except excerpt here. So what I'm going to try here is basically it's checking whether my count is an integer, else it'll just pass on, because the count is not a member, so we silently discard this item. So when we go to the try section, we calculate the total count by group, but via this command. So what this does is within the group we are iterating towards the group, and we are basically summing all the counts, and then we get the total count for that particular group, and the group is identified by its current word, right? So if that word which has a total count is greater than a max count, we basically keep that as max, and we keep note of our max word is the current word, right? And we know that a word, the minimum, uh, basically the minimum frequency can only be one, because a word can occur only once as minimum, because there's no zero, there's no negative, right? So if it's a if it's one, then I'm going to print out all the words that have occurred only once throughout the file system, right? So that's my reducer.py. So now what I'm going to do is I'm going to run the same program, same Hadoop job for the 1 GB text file to find the max and the minimum minimum frequency words, right? So same steps, we basically copy the local file system on our Hadoop. So this is our directory that is supposed to be on Hadoop, and we're gonna name the file system as Gutenberg 2. I misspelled. Yeah. So after I do that, what I'm gonna do is I'm gonna run the program. So I just copy pasted, so there might be some extra white space in between which I need to correct. Yeah. So before I run this job, I just want to show that our file system has been created. So I'm going to just reload this, and as you can see, Gutenberg 2, and you can see that this text file is of 1 GB, right? So let's run this job. So again, this is going to take a lot of time. This is going to take a lot of maps and reduces, and I'll pause the recording here, and once it starts mapping, just so you know that it has started mapping. Yeah, so it started mapping, so I'll pause my recording here, and once the process is complete, I'll resume the recording. So the job has been completed. So basically getting the max and the min from the 1 GB text file, and just to confirm that it is completed successfully. Yeah, so the first job corresponds to the 1 GB text file, and the second job corresponds to the three files which we had around, which had 1.5 MB max each, right? So as you can see that the estimated time for the three files job, it was around 30 seconds, right? Roughly 33 seconds to be exact. And for the 1 GB file, it took around 17 minutes roughly to basically get the max and the min frequency words, right? So we can estimate the performance over Hadoop here, right? So we can see that here as well, that we can see a new output, that is Gutenberg output 2, which has the output file. So I'm just going to run a couple of commands. I'll minimize this for now. So what I'm going to do is I'm going to basically get the output of the file basically, right? So sdfs minus ls, two, right? That's the name of my directory, and we could see that it's a success, and the file name is part 5 times 0, right? So I'm gonna get the output. Two, three, 4, and 5. Yeah. So this is gonna basically print out all the words. So as you can see, the word was occurred 42097 times, and all these words are basically, oh, one sec, did I run the, yeah, sorry, I ran the previous output, that's what I was wondering. Yeah, this is our output file, right? And now if I do this, so the words that are being printed are the words that occurred only once, right? And the word with max frequency is actually 9736298, which is again the. So we performed our first task, that is to do the word count with the max and min, and doing this for the 1 GB text file. That's the purpose. That's the first step. Now the second step is to do the same thing on MPI and then compare the performance, and then do another program on Hadoop and MPI. Before I execute, I'll just show what the mapper and the reducer program is doing. So the mapper, I'm importing a thing called counter. So the counter is like a sub dictionary which counts the number of characters in a string. Basically, that's how I'm treating it, right? So in addition, so I am using iterators and generators because I'm using yield, and this is my generator function. If I have a yield on a function, that makes the function as a generator, right? So the read input is same as before. The read word is now will get a word as an argument, and then the counter will basically give me a sub dictionary, which acts like a dictionary. It's like a subclass of a dictionary with the corresponding count for that particular character, right? And I'm yielding the key value pair uh, in this particular function. So this becomes a generator function again. So we are using iterators generator so that it's more quick. And let's get to the main program. So main read inputs is .in, same as before. For words and data, same as before. We iterate over the words, and then for each word, I would call that read word function. The scar count will be a basically a key and a value, and through this I'm getting a char count. I'm printing the char and the count, and my separator is my tab, right? So this is my mapper. So this will basically output the number of characters in a word by word. So suppose my text file contains foo bar, right? FOO and BAR. So this will produce O as 2, F as 1, and then B as 1, A as 1, and R as 1. And then if it's again a foo bar foo, then it will produce O as 2 and F as 1 again. So essentially, looking at the words perspective, I am doing my character count per word on my mapper, and then I'm giving the responsibility of the reducer to count the overall characters in my whole uh, basically file. So this will produce a character count pair on my std out, and that will be taken as the input for my reducer. So let's check the reducer code. So it's taking a lot of time. Sometimes happen if I'm running it for a long time. Yeah. Sudo nano reducer by. So when I do that, yeah. So this is also same as before. Uh, Again, this is also a generator function. I'm using yield, and this basically giving me a split with a char count pair. Now I'm declaring a defining a dictionary as char count. Why? Because ASCII characters are only 128 in number because it's a 7-bit ASCII code, right? So there are only 128 characters, ASCII characters. So I won't be running out of memory. That's what I'm trying to say here. So I'm using a dictionary here to keep track of all my characters, right? Data is equal to read mapper, same as before. I'm using the same group by logic. It'll group based on the character. Earlier we used as word, but now we're using as a character, right? So my current char is basically the key character, and my group is based on that particular key. That is the current character. right? So I'm calculating the total count same as before, and then I'm putting it in my dictionary, right? So after I do that, I print out the basically key value pair, and I'm also printing the max and the min value for that particular whole of the file, right? So that's how I'm. So basically, my mapper is just uh, giving me the number of characters in a word for each word, and reducer is basically clubbing it and basically giving me the total count for all the characters, right? So that is reducer.py. So with my modified mapper and reducer for the character count, um, I'll run the Hadoop job for the 1 GB text file. So I've already deleted the output file so that we could generate a new file. Let me show you that. As you can see, there's only Gutenberg 2, which is the file system that has my 1 GB text file, but there's no output file for that because I'll be generating that, right? So let's run the job. This is going to be my 2, and this is going to be my 2. Right. So same process. This is going to take some time. It'll do some maps and reduce, and since it's 1 GB file, it's going to take a lot of time. So I'll pause my recording here and I'll resume once it's done. So you can see that the job has finished, and just to confirm that the job is finished, we'll see the GUI, and as you can see, it took around more than an hour actually to basically count the number of characters in a 1 GB text file, right? And we can see that the output directory has also been created, that is Gutenberg hyphen output 2, right? So we're going to view the output file. STFS-cat, this is output 2. So as you can see that our character with maximum frequency E is around this much, and the question mark is around 12. Right? So that concludes the Hadoop version for the character count and word count, and Kaishavi will take the demonstration video for the character count and word count for um, MPI. Thank you.
Now let's see how we can apply or calculate word count in MPI. So we have written the code in C++ language, and here the struct pads is the structure for sending and receive data of word count. The count is the number of count, and the word character word array is for the word. So we are using hashmap here to keep the track of the count of the word. So let's see what is the logic of our code. So first we will open the file in the process 0. We have printed some statements like opening the file and open the file to keep track of at which stage we are in the code and the work. So first we have read the file. Here let's go to the function read file. We are reading the file in chunks of buffer size. So we are not reading the whole file of 1 GB at a time. We are dividing it into the chunks, and then so process 0 will read the file into chunks, and then we are splitting that chunk into lines, number of lines, and according to the processors we are dividing those number of lines to each processor, and allot a total number of lines, particular lines to each processor, and then send that data to that particular processor using MPI. So here we are first sending the size of the chunk to the process and then the chunk of the file. Now the processors will receive the size of the data to process, and afterwards it will allocate that much of memory to a buffer and then read that data into it. After that, we are defining a hash map in which our key is the word and the value is our count of that word in that particular file. So we are using str to tok to splitting the words from the line, and then using a hash map we are keeping the count of each word in the value and the where the key is the word. Now we are sending that back to the process 0, and then we'll combine all the hash maps into a final hash map. Then we are finding the maximum number of count and the minimum number of count and printing it on the console. We are keeping the track of the time to execute the code using W time, which is there is an inbuilt function of MPI. So this way we have implemented word count in MPI. Same goes for character count. The only difference is that we are calculating the character counts by splitting the word into its characters, and same here. Uh, Key is the character and the value is the count of that character in the file. Same as word count, we are calculating maximum character count and the minimum character count and split and printing that on the console. So now let's execute the code of word count in MPI. I have already created executables on each of the VMs, and we are using total 6 processors because each VM has 2 processors. Here I have given 6 input processor. I'm executing this code on 1 GB file. So as we have seen in the code, message received from 0 to process 1, we are dividing the file to each processes to count the words in that particular chunk of the file. Now we are waiting to create them hash map. It will take a while because the file size is much bigger. See, hash map is ready in process 2, 1, 3, 4, 5 because it is running in parallel. So now we are merging the hash map into one. So we can see the minimum word count because we have so many single word in a file, and at last we'll get the maximum word count. So we can see that it is being executed in 109 seconds only, and the maximum word count is which is 9794996. So this way it is taking much lesser time than Hadoop. So now we will execute character count code on MPI. We are using 6 processors to divide the file in chunks. So it is sent from process 0, and the chunks of the file are sent to process 1, 2, 3, 4, and 5. They have received that chunk, and now they are calculating hash map for the character count. It will take a while. So hash map is ready for all of these processes. Now they got the character counts, and the minimum count is 12, and that character is not being printed because it is not compatible. And the maximum character count is E, and it has taken only 68 seconds to run this code and calculate the character counts of the file of 1 GB. So it is much lesser than Hadoop. So we have seen the working of MPI and Hadoop for calculating word count and character count of a file. So let's compare MPI and Hadoop. So in MPI, user has accessibility to the low level of the system, whereas Hadoop is user friendly and easy to learn. So in MPI, we have more control on the hardware because we can code in the low level languages like as C and C++. We can access the memory with that, and we can also divide the works to various processes as we want. While Hadoop does everything for the user, so user does not require to know in depth of the hardware or working of delegating the work to the processes. And so from this experiment, here we conclude that MPI takes very much lesser time to execute a code or completing a work than Hadoop, but Hadoop is much easier to implement for any user and very easy to learn. So hence we have completed this lab successfully. Thank you.